Hi friends, in this video we'll learn about the force between current carrying wires as well as how different current carrying loops behave when they are placed in uniform magnetic field. First of all, you have a wire here carrying current IA and another wire carrying current IB. You know that the magnetic field due to these currents here will be first of all, magnetic field due to A will be mu naught IA, that is the current, and here 2 pi, let the distance be d, they are separated by a distance d, so here comes 2 pi d. You know that this is the formula for magnetic field given by a current carrying wire. Okay, this is the magnetic field due to the wire A at the points on this wire, at any point this points. Of course you are assuming these two wires to be very long. Okay, now because of this magnetic field, the direction of this magnetic field will be into the screen. Due to this magnetic field, the wire B experiences a force, right? And that is given by ILB, as you know. Force on B due to magnetic field A will be current of wire B into, say I want to calculate the force on particular length L, let it be L. L and the magnetic field here is BA, right? Same thing I can write it as IB L, and instead of BA I'll write mu naught IA by 2 pi d. So this is the formula for force uh, on on a length of L, on wire B of length L. Now instead of that I'll write the force per unit length. So force on B due to A, as you know, is mu naught IA IB by 2 pi d into L, right? So the force per unit length will be, just remove that term. This is easier to remember, and this looks nice even. This is force per unit length. Okay, and note that FBA will be equal to the negative of FAB. I mean to say that the force on B due to A will be opposite to the force on A due to B. Observe this. The direction. What will be the direction of this force? See, current is in this direction, and magnetic field goes into the screen. So by right hand rule, the wire B experiences force in this direction. I mean, it is getting attracted to the other wire. And if I take the other situation, I want to calculate the magnetic field due to B. At this point, it will be in this way. So the current here is this way. So the wire A experiences a force in this direction. It gets attracted to the wire B. So the forces are in opposite direction. That's what is the meaning of this statement. And what can you infer from this? Since the currents are in the same direction, or they are parallel currents, I should say that they are getting attracted, or remember it this way: parallel currents attract each other, and anti-parallel currents, they repel each other. So if this was the situation, then the forces would have been like this. Okay, hope everything is clear till now. And this is the main formula that you have to remember. And actually this is how ampere is defined. Observe this formula. Here you have mu naught by 2 pi, right? So I'll multiply by 2 and again here divide by 2, so that I'll get this mu naught by 4 pi. And observe this. If I have two wires, two very long wires separated by distance 1 meter, and if I pass equal currents through them in same direction, and if I'm able to get the force per unit length as 2 into 10 power minus 7 Newton, then I can say that the current through each wire is 1 ampere. This is how an ampere is defined. Now let's move forward. Observe the situation. This is a current carrying loop. Let the current be I, and these are north pole and south pole of magnets, so that they give some uniform magnetic field in this direction. Okay, and Let us see how this loop reacts for this scene. Observe that current flows here in this direction, as well as magnetic field is also in this direction. So there's no force here because of this part of wire, and the same thing happens here also. But see here, see what happens here. For let me name this A, B, C, D. Due to BC and AD, there is no force, right? But due to AB, there will be a force, and it will be, if we see the same loop from this direction, it will appear to me as a line. Okay, this is A and this is D. Of course, behind A is B and behind D is C. And the force on AB due to this magnetic field will be in this direction by right hand rule. Let it be F1. And similarly, the force on CD due to the same magnetic field will be in this direction, right? Let it be F2. And note that the magnitudes will be same. Let the length of this rectangle be B, and breadth, let the breadth of this rectangle be B and length be A. So this is A by 2 from here to here, and this is also A by 2 if this is the center. So because of these forces, this rectangle tries to rotate in this direction with some angular velocity. Are you getting me? Now the torque, let it be tau. It will be F1 into A by 2 here, and there's one more term, F2 into A by 2. Now I can write F1 as I into small b into capital B A by 2. You know the force is ILB, right? The current is I here, and the length of that part AB is breadth B, and IL magnetic field is B. And as I have A by 2 term here, I'll write A by 2. And similarly, actually the F1 and F2 are equal in magnitude. I'll get the same term here. So finally I have I, A, B and B. This is the torque. Now AB is what? AB is my area of this rectangle, right? So the same thing I can write it as tau into tau is equal to I capital A capital B, where A is my area and B is my magnetic field. Okay. Now what if the situation is something like this? After some time the loop becomes like this. Okay, it gets tilted and the magnetic field is in this direction. Of course this is center. Now what happens? You'll have a force like this and you'll have a force like this. Now F1 will be equal to IBB only, and F2 will also be the same, but the torque, it will not be the same. Let it be T naught now. Torque will be different, right? It will be F1. It was A there, it was A by 2 there. Now it will be A by 2 sine theta if this is your theta. Hence, and this will also be theta, and this will be your A by 2 sine theta. So this will be the torque contributed by force F1, and similarly you have F2 A by 2 sine theta. So what can I write the new torque as? I can write it as the same I AB capital B, but I have to write sine theta here, or in other terms I can say that I capital A capital B sine theta. What happened here? When the loop is tilted by angle theta, then the torque got multiplied with sine theta. So observe this, the torque can be written as I capital A capital B, right? So the same thing I'll write it as M cross B, where M is known as magnetic moment and it is I times the area. Note that M is a vector, so here area is also vector. The units are ampere meter square. Now how to get the direction of area of current loop? See, if you have any loop, say carrying a current, then if the direction of current is given by your curl of right hand fingers, then the thumb points the what area. That's it. Now you know how to get the direction of area. Now you know what is magnetic moment. So this is a vector, this is a vector, and torque is given by the cross product or vector product of magnetic moment and magnetic field. So from this you will get IAB sine theta. You can get it right. Okay. Now torque vanishes when theta is equal to 0. There the net force will be 0, as well as the net torque will also be 0. And if the magnetic moment is parallel or anti-parallel to this magnetic field, then also the torque vanishes. In this scene, because my current is going in clockwise direction, so from right hand rule I can say that my magnetic moment is this one. Are you getting me? So my theta is the angle between magnetic moment and magnetic field. Okay, hope everything is clear till now. Let's move forward. Let us see how a circular loop, so current carrying circular loop, can act as a magnetic dipole. Before 2 videos or 3 videos, I don't remember exactly, I have derived this formula for a current carrying circular loop. The magnetic field at a point which is at a distance x from the center will be this one, square plus r square whole power 3 by 2. Of course, the point on the axis of the circular loop. I mean, if this is your loop and this is your current direction, and at this point P, which is at a distance x from the center of the loop, you will have the magnetic field like this, and the direction is given by the right hand rule. Here it is in this way. Okay, only horizontal. Now, what if r is very less than x? I mean, if you are dealing with distances which are very great, very large when compared to the radius of that loop, then what happens? You can neglect the r term here, and finally you can write the same b as mu naught I r square by 2x cube, right? Hope this is clear. Now, what I'll do, I'll write the same formula in terms of magnetic moment. Okay. So the same formula can be written as mu naught m magnetic moment by 2 pi x cube. What have I done? I have multiplied with pi and divided with pi so that this becomes my area, and current times area is my magnetic moment. And in denominator I have got 2 pi x cube, and I'll again divide it with 2 and divide and multiply it with 2. I'll multiply and divide with 2 so that I want to get this mu naught by 4 pi term, because that is my well-known constant, 10 power minus 7. So what have I got here? Mu naught by 4 pi into 2m, 2 times magnetic moment by x cube. Don't you feel this is something similar to the formula of electric field that we have learned in electrostatics when it is the case with the dipole? There the formula was 2p, where p is the dipole moment, and in denominator you have this thing. Here the constants are different, but the p dipole moment is replaced with the magnetic moment, and here you have electric field, here you have magnetic field. So note that analogy. That's it. Hope everything is clear till now. Keep watching.